Hello everyone. In this lecture we will be discussing about the principal stresses and the method by which they are evaluated. This method is known as Mohr circle, a very popular method. And so first of all, let's understand what exactly principal stresses are and why they are important. Then we will go through the method of Mohr circle. So we know that the designer's requirement is to know the value of maximum normal stress, maximum shear stress at a particular point. Like if we discuss our popular example of a beam being loaded by a load P, and let's say a designer is required to find out the failure stresses occurring at this point. Let's say this point is S. So a designer's requirement is to find out the failure stresses occurring at this point S under the action of load P. So what will he be requiring? He will be requiring the normal stress at this point, the maximum normal stress, and a maximum shear stress. These two requirements are important. So we will take the maximum normal stress, see the maximum allowable normal stress for this material, and then compare the two, and then he will design his beam accordingly. So these two components are most important, which are them: maximum normal stress, sigma n, and maximum shear stress. These two are required. So he will be interested in knowing these two components. So now we know that there exists a stress tensor at this point, and stress tensor has somewhat 6 independent components. So among them we'll be obtaining these two. So within these 6 components, these components exist on a particular plane. These components exist on a particular plane. Let's say this is a plane. So my particular stress tensor sigma ij exists on this plane. If I'll obtain any other plane passing through this point, like this, my stress components on that plane will be different. You understand my point? So stress components differ along the normal. You know that as the normals orient at different location, the stress components differ. So in this plane, so there will be a plane passing through this point like this, like this, like this. So in this way there will be infinite number of planes passing through this point, but there will be one plane along which the stress will be maximum, the normal stress will be maximum. There will be one plane among infinite number of planes passing through this point. There will be one plane along which the normal stress will be maximum, and that plane will be known as principal plane, and corresponding stress on that plane will be known as principal stress. So rather than obtaining this in a 3D fashion, let's consider first of all a 2D example. Let's consider a plane like this, which is having a point P, and we require to obtain the stresses on this. So this point is enlarged. Let's take out this plane, and we are interested in knowing the stresses on this plane. Let's say this plane consists of several stresses: sigma x, sigma y, and your shear components. So this plane, and in the center the point S. This whole element can shrink down to this point S, or it can expand to take the shape of this point. So I have taken one plane. In this way there exist many planes, and how this plane will be existing, like this rectangle is rotated in this fashion, so there exist n number of planes. If I'll take this and rotate this rectangle in different fashions, then I will be left with different planes. Let me show you one example. Just let me show you one example. Like I have this card. Okay, so this will be having one plane. My sigma x, sigma y, sigma x and sigma y is acting on this like this. If I will be rotating this, my plane is changing. Now this plane has changed. This plane has changed, considering the same point. So I am changing my plane. So these are infinite number of planes. There are infinite number of planes. This plane is different, this plane is different, this plane is different. So there are infinite number of planes passing through this point. But there will be one plane along which the stress will be maximum. And that plane is known as principal plane. And the corresponding stress on that plane is known as principal stress. So let's find out these principal stresses and principal planes. What are they? How they will be obtained? So let's say we have this kind of state of stress given to us, and let's say we are interested in knowing what will be the state of stress at a particular angle. Let's say if this is rotated at some orientation theta, so what will be the state of stress on this plane? So this will be sigma theta, and the shear will be tau theta. So on this plane there will be a sigma theta and tau theta. I wanted to know the values of this sigma theta and tau theta. Now this is not very difficult. You know that there is something called as force balance. So you can use a force balance method to obtain these values, but this method may sound out to be very tedious. A more easy method is to find out these components are Mohr circle. Mohr circle. I should write this name with capital M because this is the name of a person, Mohr. Otto Mohr. He has developed this method to find the transform. Basically, he has developed this method to find the transformation of the stress. So this is a transformation of the stress. I don't know they will be principal or not. They will be principal stresses or not, but they will give me the transformation of stresses without any analytical expressions. So if they can give me any transformation, they can also give me principal stresses, because one of the angles will be principal plane. So they can give me. So let's now try to consider, try to know and understand what exactly Mohr circle method is. So let's draw the Mohr circle to obtain this. So for Mohr circle, we draw two axes, and we consider that this is a normal stress axis sigma plus, and this is a shear stress axis tau. So all these values will be positive here, positive here. People used to draw it like this and this. There are different ways of doing it, but I'm telling you the most general and easy way. Positive stress, positive shear stress. So these are normal, shear. So at this condition, there will be some values of sigma x and sigma y. For now, let's consider sigma x is greater than sigma y, and both of them are positive and tensile. That means they are having, so this is a biaxial loading on both the directions. So this is biaxial, and both the stress, let's consider that they are positive. So let's plot them. along the sigma x. So along the sigma x, let's say my sigma x is this, and my sigma y is, let's say, this is my sigma y. There will be some value sigma x, sigma y. As I said, sigma x greater than sigma y. This will be. Now let's plot the shear stresses, shear tau. Let's plot the shear stresses. So there will be one shear stress that will try to rotate this element. This shear stress try to rotate this element in a clockwise fashion. This tau xy will try to rotate this element in a anti-clockwise fashion. If such happens, then we consider the shear to be positive. And if any shear tries to, like this one, any shear tries to rotate the body in a clockwise direction, then we consider them to be negative. So let's say this tau is trying to rotate in a clockwise direction. So this will be positive. So let's consider that shear will be positive, since that shear is along sigma x. So along the sigma x, positive. Let's say this will be the value. So we have this as tau, and along the sigma y, this shear will try to rotate this in a clockwise direction. Let's consider clockwise as negative. So this will, so we'll be getting 2 points. We'll be getting 2 points. This point, let's say A, this point, let's say B. Now you join AB by a simple line, and considering this AB as a diameter of the circle, draw a circle from this. My circle will not be exact, but let's bear with me. I'm drawing it by gesture of hand. So let's consider this is my circle. So this circle will be called as Mohr's circle. Again I have written it in small. This circle will be called as Mohr circle. A Mohr circle represents a complete state of stress of a 2D dimensional body. Mohr circle represents complete state of stress of 2D body. What does I mean by that? That means you took any angle here. You took any angle from this 2D body in the rotation. You will find a corresponding value on the periphery of the Mohr circle. But to do this, just remember one thing, that if you wanted to find an orientation theta and you wanted to find the stress components on this oriented angle theta, in the Mohr circle you have to do 2 theta. That means in the Mohr circle the angle will become doubled, and I will tell you why that will happen. In Mohr circle the angle will become doubled. So from the baseline you can say that your Mohr circle angle will be like this. From this line, let's consider from this line a clockwise orientation. Let's consider. So this is your line, this is the diameter, and consider anti-clockwise rotation you consider. So consider at this and at this, let's say this becomes 2 theta. So the value corresponding to this will be your tau theta and your sigma theta. Your tau theta and your sigma theta, value corresponding to this. Since what happened, since we have taken this in a anti-clockwise direction, so from the diameter line take 2 theta as the anti-clockwise orientation and make a choose a point on the periphery. That point will represent tau theta and sigma theta. So we will be able to find normal stress and shear stress on this point. I hope this is very easy and clear to you. So let's look more on this. So this is any transformation of stress on the Mohr circle. Any transformation of stress on the Mohr circle. So let's consider a particular example of the orientation that we want. And what we want a maximum stress, which will be called as a principal stress. So what will be the principal stress on this? The principal stress exists along the sigma. So the principal stress on the Mohr circle is at the maximum and at the minimum, because along this periphery the maximum stress will exist sigma 1 and the minimum sigma 2. So the maximum stress occurring on the Mohr circle periphery will be sigma 1 and the minimum will be sigma 2. And what is the difference in the maximum stresses? Orientation difference. Difference between maximum and minimum principal stresses. The orientation difference is 180 degree. Remember this. This will tell you the why we have taken 2 theta here. Instead of rotating theta, why we have taken 2 theta here. The difference between the maximum and the minimum principal stresses is, the planes of the principal stresses, maximum and minimal plane is 180 degree. So by the 2 theta example, on the, let's say it will be having some orientation along the principal plane. If I'll find out the transformation along the principal planes, this will be having like this. So I will be having sigma 1 and sigma 2. This is my principal plane. And you can see sigma 1 and sigma 2. So if sigma 1 is maximum, sigma 2 is minimum. And what is the difference in the orientation? This plane is different, this plane is different, and they are oriented 90 degree. That means both are oriented at a difference of 90 degree, and that is why along this we have a 180 degree. So since the Mohr circle is represented in a kind of a circular fashion, the orientation is doubled. In this case this is 90. In the Mohr circle case, this is the difference between the two planes is 180 degree. That's the major reason of the difference. So you know that now. This particular example, this element now has been rotated to its principal planes. And this is a maximum principal stress and this is a minimum principal stress. So designer's requirement is to find out the maximum principal stress. In some cases minimum is also required, and that is also somewhere applied. So this is how the maximum and minimum principal stresses are obtained. Apart from this, what will be the designer's other requirement? To find the shear stresses. But before we go to the shear stresses, let's analyze this. If you see this is the plane of maximum principal stress. That means this is a principal plane. This axis is a principal plane. This axis is a principal plane because sigma 1 and sigma 2, the principal stresses acts on this plane. And if you analyze this plane, there is no shear stresses on this plane. Though that means shear stresses are zero on this plane. That means on the principal plane, on the principal plane, no shear stress exists. On the principal plane, no shear exists. That means you will not be finding any shears along the principal planes. So now consider what was the designer's another requirement to obtain the maximum shear stress. So from the Mohr circle, you have obtained the principal stresses. Now what will be the maximum shear stress? So maximum shear stress occurs like this. This will be the tau max, maximum shear stress. And what is the value of tau max? This is the radius of the circle, r. So radius of the circle is sigma 1 minus sigma 2 divided by 2. This will be called as the radius of the circle. This will be a radius of the circle. So this is the radius of the circle in terms of principal stresses. Shear stress tau max by this is a radius of the circle in terms of principal stresses. But what will be the radius of circle in terms of the given stresses? In terms of the given stresses, let's say I don't want to find out the principal stresses. I just wanted to know the maximum shear stress. So I will be having only these components. So from this component also I can obtain the maximum shear stresses. So let's say that this is radius r. So let's obtain the tau max from this Mohr circle. So from the construction it can be obtained very easily. We know that this, let's consider this triangle. If you consider this triangle, what is this? Hypotenuse is the radius of the circle, tau max. This is the radius of the circle. So your tau max is, by the Pythagoras theorem, equal to, what is this value? Square of perpendicular and square of base and perpendicular. So what will be this value? What will be this value? Sigma x minus sigma y. So this value is sigma x minus sigma y. And since this is equally distance from this will be sigma x minus sigma y by 2. So this value is sigma x minus sigma y by 2. So my tau max will be square root of, tau max here will be square root of this tau max, sigma x minus sigma y by 2 square minus plus tau square. So this will be my radius of the circle or tau max in terms of the components, given components. Okay, and I can also say that what will be the value of sigma 1 and sigma 2? What will be the value? So the analytical expression is sigma 1 comma sigma 2 is equal to sigma x plus sigma y by 2 plus minus, I'll prove this just now, square root of sigma x minus sigma y by 2 square plus tau square. This is sigma 1 and sigma 2. You can obtain it analytically also, and you can obtain it from the Mohr circle. So just see this triangle again. What is now required? Sigma 1 and sigma 2 is required. Let's find out sigma 1 first. So sigma 1. Let's find out sigma 1 from this side. So this is r. This part is r, tau max, radius of the circle. And what is this part? This part is known. Now what will be this whole part? This whole part is sigma x plus sigma y sigma x, and what will be this part? Sigma y, because this part and this part is same. So sigma x plus sigma y divided by 2. So from this to this you will be getting sigma x plus sigma y by 2. So sigma x plus sigma y by 2 plus r will give you sigma 1. Sigma x plus sigma y by 2 minus r will give you this. Sigma x plus sigma y by 2 is this whole, minus r, this part is reduced, so this is left. If this part is considered, then this is left. So sigma 1 is whole of this, sigma 2 is this only. I hope you have understood now this. Further, there are also, it's important to realize what will be the values of the orientation of these planes. What will be the value of these orientations? Now we know that this orientation from this plane, if we consider a principal plane, so this is 2 theta, so tan 2 theta will be perpendicular upon base. Perpendicular is t upon base is sigma x minus sigma y by 2. Sigma x minus sigma y by 2. 2 tau upon sigma x minus sigma y. And further, since we are taking it clockwise, this is a drawn line. So from this, a clockwise will give me a negative. So minus 2 tau upon sigma x minus 2 tau upon sigma x minus sigma y. So from this I can obtain theta. So I will be getting 2 thetas here. From this I will be getting 2 theta. 1 theta for maximum principal stress, the plane of maximum principal stress, theta 1 and theta 2, and the another one, the plane of minimum principal stress, and both of them will be differ by 90 degree. In one of the examples I will show you how. And further, the shear plane will be, you can consider this, let me take another, you can consider this triangle and you can find out the shear plane also. Take the orientation from this to this. This will be again 2 theta, and the shear plane tan 2 theta will comes out to be sigma x minus sigma y upon 2 tau, and this will be positive because the orientation taken here is positive. So this will be sigma x. Just find it out how this is done. You can easily deduce these two expressions from this. So we will be having 4 expressions. One tau x, how this is evaluated like this. Another sigma 1 sigma 2, the principal stresses evaluated like this. And we have the principal plane theta 1 theta 2 corresponding to the principal stresses, and we have 2 other planes theta 3 and theta 4 differ by 90 degree again, corresponding to the shear stresses, maximum shear stresses. Now let's consider one example and let's see how this is evaluated. So now let's say you have been given this example. A state of stress has been shown to you, a biaxial state of stress, on which the axial stresses along x direction, sigma xx, are 200 Newton per mm square, and y stresses are compressive, 80 Newton per mm square, and the shear stress given is 60 Newton per mm square. You have been asked to find out the principal stresses, the principal planes, the maximum shear stress, and their planes of maximum shear stress. Everything will be meant to find out from this. So now you know that. First of all, find out the maximum principal stresses. So from this we know that the maximum principal stresses sigma 1 and sigma 2 can be obtained through this. So just obtain sigma 1 sigma 2. When will you put in the values, you will be getting 212.3 Newton per mm square, and sigma 2 as 92.3 Newton per mm square. So this will be called as maximum principal stress, and this is minimum principal stress. You can just see these stresses and can easily comment on them. Maximum and minimum principal stress. Now what will be the value of the orientation of these principal stresses? So use the tan 2 theta equal to minus 2 tau upon sigma x minus sigma y, and put the values. So you will be getting theta 1 as minus 11.6 degrees, theta 2 as minus 101.6 degrees, and you can see that they differ by 90 degree. That means the orientation of the two planes, the maximum principal stress and the minimum principal stress, the orientation of these two planes differ by 90 degree. And I'll show you the graphical way of putting these stresses together also, how these stresses to be put graphically. Now let's find out the maximum shear stress. So maximum shear will be tau max, and you have the expression for the maximum shear. This is the expression, radius of the circle. Put the values and you will be finding plus minus 153.3 Newton per mm square. What will be the orientation? Tan 2 theta sigma x minus sigma y by 2 tau xy. And from this you will be getting the orientation theta 3 33.4 degrees, theta 4 minus 56.6 degrees. Again they differ by 90 degrees. They differ by 90 degrees. And since this is a maximum shear stress, so on the planes of maximum shear stress you will be having some normal stress also. The maximum shear stress planes are not the principal planes. Principal planes are these planes, and on the principal planes no shear stress exists. So these are different planes and these are different planes, oriented differently. We have obtained these because maximum shear we have obtained because this is the designer's requirement. People require, if the material fail in shear, what will be the maximum value of that shear. So we have obtained that. So on that plane there will be normal stress also. So the normal stress on that plane will be, in terms of component, sigma x minus sigma y by 2, and this is 200 minus 80, this will be 60 Newton per mm square. Now you have obtained all these values. Sigma 1 you have obtained, sigma 2, theta 1, theta 2, tau max you have obtained, theta 3, theta 4, and normal stress on the shear plane. So first of all, let's draw the orientation of sigma 1, sigma 2, and these theta 1, theta 2. So let's draw here. So let's draw the orientation. So now we know that the orientation is somewhat, so your plane is like this. And since this has been now now this plane is being rotated like this. This was earlier, now this is rotated at some angle. What is that angle? This is rotated by, in a counterclockwise direction, in this, and this is minus theta 1 minus, sorry, not a counter, this is a clockwise direction, minus 11.6 degrees. And the stress on this is principal stress, sigma 1 equal to 2013.3. Whenever you do these problems, please represent these stresses, especially the principal and these stresses, please represent them. This will be better for the examiners to check also. And the another stress is the compressive stress. As you can see here, minus 92.3. This is compressive stress. Once we have said the orientation as compressive, we don't need to write the minus sign. 92.3 Newton per mm square. And what will be its orientation from the horizontal? This is my orientation. This is minus 11.6, correct, and this is my new plane. So overall orientation is 101.6 degrees, and this is definitely, this is 90 and the rest is 7.6. So this is how is represented. Also represent the stress here, sigma 1 with the same value, 2013.3 Newton per mm square, and represent the other stress also. These all are perpendicular. The important thing to take out from this is the theta 1, theta 2 values are with a difference of 90 degree. So this is a plane of maximum principal stress, sigma 1, and this is a plane of minimum principal stress. So these theta 1, theta 2 values are not important. The important thing is both the planes rotated, both the planes differ by an angle of 90 degrees. These theta 1, theta 2 values help us to achieve this particular configuration. So it's not important to say that theta 1 is directly associated with sigma 1 or theta 2 is directly associated with sigma 2. You just have to say that sigma 1 is oriented at minus 11.6 degrees to the downwards from the reference plane. In this way it can be said. Now let's come to the shear values. Shear values will be maximum shear stress we need to represent, and now how you are making this plane? You make this plane according to the orientation angles that are given to you. Now we know that the orientation angles is somewhat, so this orientation will be somewhat 33, positive 33. This is, there will be shear like this, so there will be shear like this. What will be the values of this shear? Tau max plus 153.3 and the another one is minus. So this is 153.3 Newton per mm square, and this orientation is 33.4 degrees, and the normal stress on this, since it has a shear, maximum shear, so maximum shear occurs on this plane which is oriented at 33.4 degrees in an anti-clockwise direction. So this plane exists. And what will be the value of normal stress on this? We have already calculated sigma n 60 Newton per mm square. Is it right? And the other orientation angle, other plane is minimum shear, and that is oriented at minus 56.6 degrees. Again the difference is 90 degree only. So these are the two values. Remember that the shear values are same, 153.3 positive and 153.3 negative here, 153.3 positive, 153.3 negative here. So these will be the values. So I hope you will be having a good introduction to what the principal stresses is and what is the importance of principal stresses to the designer's point of view, and this 2D method of obtaining the Mohr circle. Remember that the Mohr circle can also be extended to the three dimensionals also. So you can extend the Mohr circle to 3D also to obtain the state of stress, the three-dimensional state of stress also. In the next lecture we'll be seeing a rather easy method of eigenvalue analysis, which will be determining the principal stresses. So I think this is enough from this one. Thank you.